Good day, class. So for today, you're going to learn something new about differential equations. Now, actually, this is already the second half of differential equation. The first half was about first order differential equations, and this one is the second half, higher order differential equations. In here, we're going to learn how to determine the solution of a higher order differential equations. We will learn also how to classify higher order differential equations in terms of linearity, and we will also know how to classify higher order differential equations whether they are homogeneous or not. So knowing whether your differential equation is homogeneous or non-homogeneous, linear or non-linear is always the first step in determining the solution of such higher order differential equations. So let me start with a slide showing examples of higher order differential equations. Now here in this example, you have the third order derivative as the highest order derivative present in this particular differential equation. So it is a higher order differential equation. The next thing that you will look into are the coefficients of the derivatives of your unknown function and the unknown function itself. Now, in this DE, your unknown function is y and your independent variable is x because your derivative is dy dx. And that's something that you have learned already in prelims. So, as I've said, you're going to look into the coefficients of these derivatives and the unknown function itself. So, in here you have a constant 3. In here, you have 5x, which is a function of your independent variable x. In here, you have negative e raised to x, also a function of your independent variable x. And in here, you have another constant, which is 7. Whenever the coefficients of the derivatives of your unknown function and your unknown function itself is a constant or a function of the independent variable for a higher order differential equation, the said higher order differential equation is linear. So this one is a higher ordered differential equation which is linear. Now if we go to the second example here, more or less the first, the second, and the first term on the right side of the differential equation are the same. Actually, they are exactly the same. So, the first two examples only differ in the coefficient of the first derivative of the unknown function and the unknown function itself on the last term. In here, you have a y, but in here, you have a y squared. Now, in here, you have a negative 1. In here, you have a negative e raised to x. The primary difference of these two differential equations actually is the exponent of the unknown function y. In the first example, the exponent is 1, and the second example, it is 2. So, whenever the unknown function of your differential equation has an exponent other than 1, so in this case, it's 2, that makes the said differential equation a non-linear differential equation. So this one is said to be a higher order non-linear differential equation because your unknown function here has an exponent other than 1. Should any of your derivatives here of your unknown function have an exponent other than 1, it will also make this particular differential equation non-linear. Now, this very short example has the second order derivative of y with respect to t, and you also have the first order derivative here, and you have the unknown function itself. Now, the coefficients are all constants. So, this one, just like the first example, is a linear higher ordered differential equation. Now, as for this particular example here, again, quite similar to the first two. So the similarity is in the first two terms on the left side and on the only term on the right side of the equal sign. If you notice here on the third term on the left side of the equation, the derivative of your unknown function is multiplied to the unknown function itself. Now, whenever you have such a scenario wherein the derivative of your unknown function is being multiplied to the unknown function itself or to a function that is having y as its argument, the said differential equation is non-linear already. So this one is also higher ordered, but it is non-linear because the derivative of your unknown function was multiplied to the unknown function itself. As for the one that you have here, I think the highest ordered differential equation on my examples in this slide, all the coefficients are constants. So we say that this differential equation, like this first two in here, is linear. It is also linear, and it is of course higher ordered because you could see that the highest ordered derivative is 4. Now, our last example here again is quite similar to the first three and most likely very similar to the second example here in terms of what's written on the first three terms on the left side of the equation. The right side is also the same. The only difference is in the multiplier to the 7. So in here your 7 is multiplied to y squared, and here your 7 is multiplied to cosine of y. Your unknown function this time is an argument of a transcendental function, a trigonometric function cosine. So whenever your differential equation has its unknown function as an argument of a transcendental function. So by the way, what are transcendental functions? Trigonometric functions, inverse trigonometric functions, hyperbolic functions, exponential functions, logarithmic functions. Those are examples of transcendental functions. So transcendental functions have arguments. Now, if the argument of such transcendental function when written in a differential equation is your unknown function, that makes that particular differential equation non-linear. So based on our 6 examples here, you could see that this one is non-linear, this one is non-linear, and this one is also non-linear. The rest are all linear. So we have these 3 as examples of higher order linear differential equations. So this slide classified our higher order differential equation in terms of linearity. So hopefully you will remember how to distinguish or discriminate a higher order linear differential equation from a higher order non-linear differential equation. Now, we can also classify our higher order differential equation as either homogeneous or non-homogeneous. And this is our primary basis in determining the kind of procedure that we will use in determining the solution of our higher order differential equation. So we can classify it as linear or non-linear, and this time now we can classify it as homogeneous or non-homogeneous. The question is, how do you tell whether your higher order differential equation is homogeneous or not? The y's here that you see in the 2 forms of the differential equation represents the derivative of your unknown function, because the exponents of these y's here written in terms of n, which is a whole number and is positive, represents that derivative of the unknown function. So this y raised to n enclosed in a parenthesis is actually to be interpreted as the nth derivative of y. So this is also the n minus 1 derivative of y. This is the first derivative of y, and so it's the same thing with this. So if you look very closely, it's so easy to tell actually which of the two is homogeneous and which one is non-homogeneous. So if we will proceed, the non-homogeneous is the second example and the homogeneous is the first one. Now, can you see the difference between the two forms? Actually, it's very obvious. In here, in the non-homogeneous, what is written on the right side of your differential equation is an expression which is a function of your independent variable, or this could even be a constant, whereas the first one has 0 for the right side of the higher order differential equation. When the left side is written in this form already, that is, you have derivatives of your unknown function and the unknown function itself having coefficients which could either be constants or functions of your independent variable x. These two then are the same of what appears here on the left side. They differ only on what's appearing on the right side. So it is homogeneous. The higher order differential equation, that is homogeneous if your g of x on the right side or your function of x on the right side is equal to 0. Otherwise, we say that our higher order differential equation is non-homogeneous when what is written on the right side is a function of the independent variable or is a constant. So remember that. Now, as examples, so you could see here in the first example that the last term is a negative cosine of x. In the form here above, for the two types or classification of higher order differential equation, functions of x alone or expression which is a function of x alone should appear on the right side of the DE. Whereas what appears on the left side are products of your unknown function or the derivatives of your unknown functions with respect to a constant or with respect to an expression in terms of your independent variable. Now then, this one was deliberately, so this negative cosine x here was deliberately written on the left side of the equation to confuse you that this one is a homogeneous differential equation. At first glance, you will say this is a homogeneous differential equation. But if you look very intently, it is non-homogeneous because this negative cosine of x here should be in the first place transferred to the right side. That way, it will conform to any of the forms here, which should end with the unknown function multiplied with a function in terms of the independent variable. So as you can see, this one is non-homogeneous, while this one is already homogeneous because the last term here is a product of a constant and your unknown function. So then, don't be confused. If you see a 0 on the right side of your equation and there's an expression in terms of the independent variable on the left, you ought to transfer it to the right side. That way, it will conform to this form or even this form in terms of what's written on the left side of the differential equation. So this one is non-homogeneous and this one is homogeneous. If you know your differential equation already, or if you're able to classify your higher order differential equation into homogeneous or non-homogeneous differential equation, you can already proceed with the procedure that is appropriate for such classification of a higher order differential equation. So you have here 5 examples, and if you're going to look on these examples, examples of second-order differential equation, which is a function of x and y and the derivatives of y, then we can say that for this particular second-order DE, if we look in here, everything here is a second-order DE. Why? Because you have here the second-order derivative. So, it's a second-order DE. Our next example will tell you that the second-order DE is also at the same time linear. So, based on the requirements I have stated in terms of the form a while ago. So, we are to look on the examples here on the left side which will qualify as second order at the same time linear. So, if you see this one, that's okay. This one is never okay. This one is also okay. Same thing with this. Same thing with this. So, let's check if that is correct. So, now your example A, C, D, and E are second order and linear because A, B, C, F are functions of x only or could be constants. Now, what about second order at the same time homogeneous and linear? Now, second order, everything here is second order. Homogeneous, the right side should be equal to 0. And linear, meaning no term in your left side of the DE should be multiplied or in terms of your dependent variable or your unknown function itself. So, in this case, if it's homogeneous and linear that we're looking for as an example, that would be the last two. So, D and E. What about if we are to look for a second order homogeneous and linear differential equation and there's an add-on with constant coefficients, meaning the coefficients of your unknown function and your unknown function itself should be a constant or a function of your independent variable x. So, if you look very closely, class, only one specific differential equation falls under this particular type, wherein all three characteristics were spoken: homogeneous, linear, with constant coefficients. So, if you have already taken a look, actually, the answer would be letter D. Only letter D here is second order, homogeneous, linear, with constant coefficients. So, all coefficients are constants. Now, knowing how to classify higher order DEs, now you are ready to know how to find the solution of such higher order differential equations. Now, so if your higher order differential equation is homogeneous, linear, and with constant coefficients, we can find its solution using a set of procedure. Actually, it's just a three-step procedure, and then the solution of the higher order differential equation will be very much dependent on the nature of the roots of the characteristic equation. What is that characteristic equation and roots? So, we will learn that in the next slide. So, in here, in our example, so this is the only DE which is homogeneous, linear, with constant coefficient. And in this case here, in my example, the two terms that should appear in the general solution of your higher order differential equation should contain the exponential function 2e raised to 2x and the exponential function e raised to 3x. Now, you may ask, why? How did it came about that we have these two terms that should appear in the general solution of this homogeneous linear differential equation with constant coefficients? That brings about the procedure that we ought to do. So the first step, we have to know whether our DE is homogeneous, and we have to know that, or we have to check that the coefficients of the derivatives of your unknown function and the unknown function itself are all constant. So P sub O should not be equal to 0. P sub 1, P sub 2, and P sub n are said to be constants. It's homogeneous because the right side is 0. If you're able to tell that this one in terms of form is homogeneous, then you can go to the next step. The next step will change or replace the derivatives of your unknown function by the operator capital letter D. We call this as the operator, and this is representing the derivative of y, if y is your unknown function, with respect to x. This operator is said to act or operate on the unknown function y. If your unknown function is not y, then you just have to simply change the y into that particular letter. Now, you could see now that the original here, all derivatives were replaced by the operator d. Correspondingly, the exponent of this operator d is representing the order of the derivative. So this is d raised to n, a d raised to n minus 1, a d raised to n minus 2, and so on and so forth until you have the last term, which is your unknown function, multiplied to another constant. And by the way, class, it need not be that, for example, if your highest order derivative is 5, you should complete all 5 derivatives as well. It could be that you will have the 5th derivative, but the 4th derivative is not present in the equation, but you have the 2nd derivative and the 1st. That is still okay, because in terms of form, it still conforms to this general form. So the only thing that is very important is that the right side is 0, and that you are able now to replace all derivatives with the operator d. So what happens here on the second line is the y that is common to all the terms was factored out, leaving an expression which is solely a function of the operator d. That is why you see the f of dy, because this one is your f of d and that's your y. Okay, the purpose of this is that you can replace the f of d expression to f of m and equate it to 0. Then determine the roots of such polynomial in m. So what do I mean? Now, if this is your second order differential equation and you have already written the characteristic equation, from that characteristic equation you can find the roots. The roots tell you the form of the terms that should appear in the general solution of your higher order differential equation. But what is this characteristic equation? So I will go back here. The function in terms of the operator d will be changed to an f of m. You just simply replace the d by m and then equate such expression to 0. The f of m equal to 0 here is said to be the characteristic equation. The next thing that you do is you are to find the roots of such characteristic equation, because they will tell you what type of term should be present in the solution, or specifically in the general solution of your higher order differential equation. So it's just a 3-step procedure, and it's so easy actually to follow. All you have to do is know how to determine roots of polynomials, because your f of d here, which was changed to f of m, is actually a polynomial with respect to d in the case of f of d, and in here a polynomial in terms of the variable m. So it's f of m. Now, Example in the second order linear differential equation with constant coefficients. This is second order, so we expect that our roots would also be 2. If this is third order, our roots will be 3, and so on and so forth. Just like in algebra, that if your polynomial is a 5th degree polynomial, expect 5 roots for such polynomial equation. So it's the same thing with the DE. So your number of roots is equal to the order of the given differential equation. If the roots are distinct and real, these are the form of the solution of the terms in the general solution of the DE. If it's repeated real, meaning 2 roots, you have 2 roots, but the 2 roots are the same, so we modify any of the 2 terms. That way they will not look similar. It's because your M1 is just equal to M2. So this is a case of real repeated roots. So how do we modify? We modify by multiplying one of the terms by x. If you have 3 terms here, the third term should be multiplied by x squared. So we increase the exponent of the x that is being multiplied to our exponential function based on the order of the given DE. So if the order of the DE is third order and you already have one real coefficient, or rather real roots, and the others are repeated, meaning they are not unique, they are said to be equal, then you will modify the other terms in your roots of your differential equation by multiplying it by the independent variable. If the roots M1 and M2 comes in an imaginary pair plus minus M sub 1I, this is the case in which you're dealing with the negative square root, then the form of the terms of your general solution will be coming also in terms of a pair of 2 functions, cosine and sine. The argument of these 2 functions are actually equal to the roots, the pair of imaginary roots. So actually the positive there, the positive M1 is represented by cosine M sub 1x, and the negative represents the sine. If the roots are not purely imaginary but is said to be complex, so meaning it has a real part and an imaginary part, then the form of the distinct and real and the imaginary will be connected, or will be used as one form in the case of complex roots. So the form will be something like e, the exponential function, multiplied to the cosine. That would be for m sub 1 plus m sub 2i. And again, it will be e raised to m sub 1x sine of m sub 2x. So the sine accounts for the negative m sub 2i. The cosine accounts for the positive m sub 2i. The real part of this complex root is actually the exponential function, whose argument is the real part of these complex roots, and it's being multiplied to the cosine and sine function. So the key is you have to be sure that the DE is homogeneous. Then you have to determine the characteristic equation, and based on the characteristic equation, use the appropriate form of the terms of the general solution of the given DE. Now we're ready to have specific examples on the 4 different forms of the roots of the characteristic equation. Now, let's go to the real distinct roots example. I like to present both so you can see. Now, this one, y double prime minus 5y prime plus 6y equal to 0. If you will change the derivatives to d, that would be d squared minus 5d plus 6. Then if you want to write the characteristic equation, you simply have to replace the operator d by m and equate such equation to 0. The rest is your algebra, because now you will need to find the roots of this second degree polynomial. Now the resulting roots are real and distinct, meaning they are not the same. So then the terms of the general solution will have two terms which are exponential function in forms which has the argument equal to the roots that we have determined. In terms of form class, it's really an exponential function that should be written with an argument equal to the roots of your given polynomial in the variable m. Okay, so that would be now, this will be now your two terms in your equation. So the general solution of this differential equation will be these two, but don't forget that these two should be multiplied to arbitrary constants. So this could be letter A, this could be letter B, or capital letter A, capital letter B. But I suggest that you really use the arbitrary constant C, because all you have to do is just change the subscript, then one C would be now totally different than the other C. That you are able to classify or distinguish the terms in terms of the arbitrary constant that appear. In the second example class, your characteristic equation, since this one is y double prime minus 4y, will be a simple m squared for this and a minus 4. If you will determine the roots, you have 2 and negative 2, because you will need to get the square root of 4, which is positive 2 and negative 2. The corresponding terms that should appear in your general solution again will be represented by an exponential function. So if the roots are real and distinct, even if they are repeated, are telling you that your terms will be in the form of exponential functions. So your general solution in this case will be c sub 1 e raised to 2x plus c sub 2 e raised to minus 2x. You only take the sum of these two, just like in here. But don't forget to write the arbitrary constant c sub 1 and c sub 2 in this case. Now, what about if the roots are also real but they tend to be repeated? Okay? For this example, your characteristic equation is this. If you're going to do factoring, this will be m minus 2 quantity squared. Then you will have two roots that are exactly the same. This is the time that you will modify one of the roots by multiplying it with the independent variable. If you have another root here, then the multiplier will be x squared. That way, all your terms will be unique. So your general solution in this case will be again the sum of these two with the presence of the arbitrary constant. Now, in our second example here on the right, you have a third degree polynomial. So we expect that we should have three roots. This is our characteristic equation. And this particular third degree polynomial in m will give you the roots 0, 2, and 2. These two are repeated. Well, this one is unique. So what you will do, you simply use the three roots of the characteristic equation as the argument of the exponential function. These two being the same, there's a need for you to modify one of them. This one being 0, anything raised to 0 will be equal to 1. Then you add up all of this so that you will come up with the general solution of this third order differential equation. So you have now this, multiplied to an arbitrary constant, this one another arbitrary constant, and this multiplied to another arbitrary constant. Since your solution is a general solution, it should never contain any specific constant. All the constants that should appear should be arbitrary. So as such, your 1 here should be multiplied to an arbitrary constant, which is C sub 3. Okay, this is the second case wherein we have real repeated roots. What about the third case? So let's look at the third case. So in the third case, we have, and by the way, we have another example here for a fourth ordered differential equation resulting to a characteristic equation which is also fourth degree in M with roots 0 and 1, 1 being repeated twice. So you have 3 ones. So I have already explained what will happen here. So this will be the form of the terms of your general solution. E raised to 0, which is 1. Then we have e raised to x for all the ones, 1 being the argument here of the e, and you need to modify the last 2. That way it will not be similar to the first. So this is x now, the multiplier, and this is now x squared as the multiplier for this. Your general solution would look something like this one. You add up all 4, multiplying each by the arbitrary constants. So it could be that this is the first term, this is the second, and this is the third, and this is the fourth. So it doesn't matter which one is C sub 1, C sub 2, C sub 3, or C sub 4. As long as these particular terms appear in the solution of your higher order differential equation. So now let's go to the third. The roots are said to be imaginary, and the second example will be imaginary and repeated. So let's see how it's different than the first two types. So this one will result to an m squared plus 4. If you transfer 4 here on the right side, that would be negative 4. If you intend to get the roots, that would be requiring you to get the square root of negative 4. The square root of a negative number will always have the imaginary unit I. And as such, we call this a pair, a conjugate pair of imaginary roots. So because one is positive, the other one is negative. Whenever you have this scenario, class, the terms that will appear in the general solution will be a pair of cosine and sine function whose argument is equal to the numeric value of your imaginary root. So this is 2, so this is 2x. This is negative 2, so this is 2x. The positive is for the cosine, the negative is for the sine. If this is 5, you make this also 5. As to the general solution, then you add the 2. Never forgetting that they be multiplied to, referring to the terms to an arbitrary constant. Now in this case here, you have a fourth degree higher ordered or fourth ordered DE. Now this one is a fourth degree polynomial in M, and this is your characteristic equation based on this, because this will be an m to the fourth plus 8m squared plus 16, which will result to this expression. By algebra, or using your algebra, you will have a set of 2 pairs of imaginary roots, and we say they are being repeated because you have exactly the same pair of imaginary roots. How will you alter the terms in this general solution of your DE is the same as if you have a case of real repeated roots. So for the first plus minus 2i, this is your term or this is your pair of terms. And for the other plus minus 2i, you now modify the first set by multiplying it by x. Okay? If you say, for example, have another plus minus 2i, then you will have your x squared cosine 2x, x squared sine of 2x. That general solution would still be the sum of all the terms that were written here. Okay? Now, another example is this. This is not anymore factorable. It's different than these two, because these two can be processed without having to result to using the quadratic equation. So in here, since this is not factorable, our characteristic equation will also be not factorable. We use the quadratic equation and it results to a pair of conjugate complex roots. A complex root is said to be complex. It's complicated because it has an imaginary part and it has a real part. So the way you write the solution will also be a marriage or a connection between having a real root and having an imaginary root. If it's imaginary, that should be accounted for by the cosine and the sine. And these two will be here, written here. So cosine 2x, sine 2x. The way you have seen it here. And then you have the arbitrary constants. Accounting for this positive or rather negative real part will need the exponential function to be multiplied to this form for the imaginary root. So it will be now e raised to minus x, because this is minus 1, and multiplied to c sub 1 cosine 2x plus c sub 2 sine of x. Okay? Now, we have this, I think, another example of a complex root is this one. So this time, a third degree polynomial for your characteristic equation, resulting to this, resulting to, by the way, this is 1 class. This is not negative 1. So this is 1. And this is your quadratic equation. So the roots for this quadratic equation will be in the form of a complex conjugate root. Okay, a pair of complex conjugate root. So if we write the general solution, we need to account for the first real root. So this should be 1. It needs to be edited. So this should be 1. And this is that 1 here. And we need to account as well for the complex root. So its real part will be an exponential function raised to negative x over 2. X being multiplied to negative 1/2. And your imaginary part for your complex roots will be compensated for the cosine and the sine function, the arguments of which is equal to the value or the quantity of the complex root of the imaginary root rather in your complex roots. So this is now the solution of this particular differential equation. Okay, and that's it. Okay. Now, if you have any questions, feel free to drop them in the reply box in Canvas. I will have this uploaded class tomorrow because my internet connection really just improved now. And I will also post on tomorrow the thing that you will do in our asynchronous time on Friday. So everything that is written in this slide already covers our 2 meetings for this week, and that is finding solutions of homogeneous higher order differential equations with linear coefficients. Next week we will be discussing with higher order non-homogeneous but still linear differential equations with constant coefficients. So bye class.